So as we were talking about in our last section, we looked at the default options on the 4 switches. And the first portion of building the topology, again for spanning tree, was based on the bridge identifier of the switches, which is made up of their MAC address plus the priority field, where the priority field is then broken into the 2 subfields, which includes the priority number and then the system ID extension, which again is basically the VLAN number. But since in this network topology everything is default, all of the cost values, all the priority values, the selection of the root bridge was basically based on whoever had the lowest MAC address, which in this case was switch 4. So switch 4 was elected the root. This means that from the root bridge's perspective, these 2 interfaces are facing downstream, which again means that these are the designated port roles. So traffic is allowed to forward in and to forward out the designated ports. From switch 2 and switch 3's perspective, they then look at what are the possible cost values I can use to reach the root. Or if I go this direction, my cost was 19. If I go in this direction, the cost is 19 times 3, because there's this hop, and this hop. This means that from switch 2's perspective, it says that this is my root port. Same thing happened on switch 3. Now it's up to switch 1 to choose which of these interfaces is it going to forward based on. Since both of them are equally 2 hops away, the cost values are 38 on each of them. So twice 19. Means that switch 1 now needs to do a tiebreaker between these 2. So we first look at the root path cost, or basically what's the end-to-end cost to reach the root. If there's a tie in this, we look at the lowest bridge ID. And the bridge ID is going to be of the next hop neighbor, whoever is upstream. So now switch 1 is going to compare the bridge ID of switch 2 and of switch 3. When we looked at the MAC address values, it turned out that switch 3 had a lower value. We're comparing 001B to 000E. It means that switch 3 is preferred. That's why switch 1 is choosing this as the root port. Then it needs to ask switch 2, what is your root path cost as opposed to mine? Switch 2 is saying my cost to get there is 19. Switch 1 is saying my cost to get there is 38. It means that this port is closer to the root, which means it becomes designated port. And this one here, this one becomes the blocking port. This is why when we looked at the MAC address table, if we were to go to switch 3 and say, show MAC address table, show me the dynamically learned MAC addresses inside the VLAN 1 table, it said to reach router 1, I was sending my traffic in this direction, because router 1's up here. To reach router 6, which is over here, it's going to be using port number 19. Where eventually you'll see that these addresses disappear out of the CAM table after a certain timeout. So when router 1 sends a packet again to router 6, the table should be refreshed. And switch 3 should now know this address, that it knows that router 6 is located on port number 19. So let's say now that we want to change the selection, that we don't want switch 4 to be the root anymore. We're going to change the root so that it's at the top of the diagram, so it's on switch 1. The key again is that this election is based on their bridge IDs, which is made up of the priority, the system ID, and of the MAC address. Out of these 3 values, we can't change the MAC address and we can't change the system ID, so we can change the priority. And it's a lower value that is preferred. This can get sometimes confusing when you look at some of the books or the documentation that talks about this, because a higher priority is a lower numerical value. Where the highest priority is 0, the worst priority or the lowest priority would be 65535. So a lower number is a better priority. Configuration-wise, there's 2 ways that we can change this. we have the spanning tree VLAN priority command, which again, since we're running per VLAN spanning tree, we have a different path selection for the different instances or the different VLANs. We could change it with this command, or we could use the root command. The difference between these is that the root command, this is a macro. What it does is it looks at the current root bridge priority and simply sets its own to be a lower value. So it's an automated way of doing it. The end result of it in the configuration is going to be this command, just that this option is a little bit easier to use because you don't have to keep track of the actual values that the switches have. If I were to say spanning tree VLAN 1 root, and I want to be the actual root bridge, not the backup or not the secondary, when we look at the result of the show run, it ran the macro to figure out that a lower value than the current one is 24,576. Question?
So it changes the priority value of that switch according to all the switches' priority?
According to what the current root bridge was.
Oh, okay.
So when we previously looked at the show spanning tree, it said the current root has this priority, so it's going to set its own value lower than this.
So now go to another one and set it to say 20,000.
Then that would be elected the root, correct. So this command, the macro only runs once. It's not constantly polling the priority values. So if I were to go to switch 2 and then say spanning tree VLAN 1 root primary, the result of this should be a lower value than 24,000. So 20,000. If I were to run this command again on switch 1, it's then going to continue to set its value lower than what this is, to where eventually someone is going to get to 0, and then that's the best possible priority. In this case, this particular version isn't going to go below this value. Let's try to set it again. This is where the logic of the macro falls apart. That if I wanted to go below what the other switch has, I'm going to have to manually change this. Let's just say instead of using the root macro, I'll say that the priority is simply 0.
What version of code is this?
12.246, so it's relatively recent. But if you want to be 100% sure that this switch is going to be the root, you simply set their priority to be 0. If we now look at the show spanning tree for VLAN 1, it says that I am the root because my priority is 0 plus the offset value, or the system ID extension of 1. So my effective priority value is 1. This means that all of my ports are designated. They're all facing away from me. The cost for me to reach myself is 0. If we were to look at the other switches now and look at switch 2 and switch 3, switch 1 inside of its BPDUs is saying, I have a cost of 0 to reach the root. So you now take whatever value is configured on your interface, add it to my cost value. That's what your end-to-end cost, or what your root path cost would be to reach the root bridge, or to reach me. We can see the detailed output for this if we look at the show spanning tree VLAN 1 detail, where this shows you all of the individual attributes of the bridge and of its interfaces. Where overall, switch 2 is saying my configured priority is 20,480 plus a system ID extension of 1. This is my MAC address. These 3 fields together make up the bridge identifier, or the bridge ID. The current root bridge has this priority and this MAC address. To reach the root, I'm using port number 15. From a physical index point of view, this is Fast Ethernet 0/13. My cost to reach them is 19. Then we see the timers that the root bridge has configured. By default, it has a hello time of 2, a maximum age of 20, and a forwarding delay of 15, which means that when we move between the different states of spanning tree, like going from down to listening to learning, and then ultimately to forwarding, it's going to take 15 seconds to be in the listening state. It's going to take an additional 15 seconds to go from the learning state. So if I were to shut down an interface and then bring it up, it's going to take 30 seconds before it can actually start to forward traffic. And this is based on the default timers. Question?
So if you change the priority, which forces the change of the route in a large layer 2 environment,
Right.
That's going to force the rest of the network to have to converge, right? Which
Correct.
would give about a 30-second outage, essentially, a loss
Correct.
of packet
Yeah.
transfer. Okay.
Yeah. So if you change the path selection, everyone has to reconverge, which means they have to go back through the listening and learning phases, and then ultimately to forwarding. Well, see, in today's networks, there's a way to fix this. You simply don't run the original version. This is the original common spanning tree specification. Cisco has extended this to run what's known as per VLAN spanning tree plus. Basically, it means it's just a separate copy on a per VLAN basis, but it runs the same algorithm as the original specification does. We'll see later there's a new version of this that's called the rapid spanning tree protocol. It fixes this problem with the convergence, because a lot of the times 30 seconds of outage is going to be a lot in the network.
So Brian, what's the advantage to changing the route based on VLAN?
Because that changes how the MAC address table can be built, and then ultimately how the traffic is forwarded. Because if we look at now, we had router 1 connected here and router 6 connected here. Previously, the traffic was going in this direction. By changing the route bridge, you're changing the reference point that everyone is building the network off of. So now these two links are going to be used. Then one of these links is going to be used. So maybe we'll go this way, where this one is blocking, or in the other direction. But the reason that you're changing it is you're trying to change the traffic flow of the layer 2 network. If you don't care how the traffic gets there, then you can just leave all of this as the default values. So when we look at switch 2, we see all the detailed information about myself and the route bridge. We also see the detailed information about the individual ports. Like this interface here, this is facing down towards the edge of the network. So we're not going to be receiving any BPDUs in that interface. It means there's no one is running spanning tree that's connected there.
I'm sorry, Brian, what command did you use to get that?
Show spanning tree detail. Where in this case, I'm looking at just the VLAN 1 instance. If you said just show spanning tree detail, it'll show you every VLAN individually. So from here, we can see some of the specifics of the different interfaces, where since on the other side of Fast Ethernet 04 and the other side of Fast Ethernet 06, we're not hearing any devices running spanning tree. So it means that these ports are always going to be forwarding. Basically, these are the ones that are pointing down towards the end hosts. I'm going to be advertising these spanning tree packets out, but I'm not receiving any in, so I don't really have to include that as part of the topology calculation. What I am concerned about instead is what are the ports that I'm actually receiving BPDUs in. This is how I can tell that this is connected to another switch. So as soon as I receive the BPDUs in, I'm going to look at the values that they're advertising, and then that's going to be part of my selection process.
Those ports would have to be in trunk mode to receive BPDUs, right?
Not necessarily. If they're in trunk mode, they'll be sending BPDUs for every instance of spanning tree. If they're not in trunk mode, they'll send BPDUs just for the VLAN that's assigned as the access VLAN.
Okay, so if that access port is in VLAN 10, it'll receive BPDUs for VLAN 10.
For VLAN 10, correct, yeah. So we could get the same effect for this network if these were not trunks. I could just say that the switch port access VLAN is 1. Then you still run into the problem that for VLAN 1, if you flood in this direction and the frame comes back, you're going to cause a loop. So the switches know that they're always supposed to send BPDUs out all of their interfaces. even the ones that go down to the end hosts, because they don't really know what the topology looks like. But based on the fact that on this interface I'm sending, but I never heard a response back in, I now know that this is basically the edge of the network. So there's no other switches down there that I need to run it with. But for those other two interfaces, which were 13 and 19, I'm sending packets and I'm receiving packets. So now these two ports are part of the calculation. This is where the switch is going to figure out what is the other device advertising, and then how do I make my path selection. Question?
Yeah, on the first, where you were sending but not receiving, you could also be connected to a block port, right?
It could be connected to a block port, right. So now I basically have two choices to forward through the network. I have Fast Ethernet 13 and I have Fast Ethernet 19, where again is these two ports here. The root bridge is up here on switch 1. So if we don't change anything, it means that this is going to be elected the root port. But we may want to know why. What are the detailed attributes that are being exchanged, and why is it choosing this interface over the other one? So before you make a change in your network for path selection, you need to know why is it making the decision it is now before I try to influence it. So switch 2 says here that this interface is connected to someone that is advertising a cost value of 0. My cost on the port is 19. So if I take 19 plus 0, this is my root path cost. For this interface here, I have a cost of 19. They have a cost of 19. So I add these two together. Since this value is higher than this one, this becomes the root port. This one can still be forwarding, but it can't be root. It can be designated forwarding or it can be blocking, but it can't be the root port because this one has the lowest cost, this first value. We see also that on the other side of this link, they're advertising us two different attributes. They're telling us what is the root bridge's information and what is your information. In this case, the designated root ID and the designated bridge ID are the same. It means that this port connects directly to the root bridge. For this interface here, there's a difference in what the root address is versus the designated bridge. This is the device on the other side of the link. So this basically means it's not connected to the root. It's going downstream to some other switch in the network. So if we were to go to the other side of the topology on switch 3 and look at the same thing, it's going to be a similar output here, that if we show spanning tree for vThen1 detail, the root identifier is always going to be the same, assuming that they're running the same copy of spanning tree. Like if there's a physical cable problem, then you could end up calculating the topology wrong, and that could possibly cause a loop in the network. But if everything is communicating properly, everyone should be agreeing on what this value is, the root ID. I then see that I have port number 5 that's part of this topology. I'm sending BPDUs, but I'm not receiving them, which means that there's no other switches on that link that's going down to an end host. Now I have two choices for the actual active topology. I can tell this because I'm sending and receiving BPDUs on these ports. If I were to say clear spanning tree counters, that's going to reset that. From this point on, we can tell, once the network is converged, which direction is the route reachable through, based on the fact that I don't send BPDUs up to the route. I receive them from them, and then continue to send them downstream out my designated ports. So I'm receiving the BPDUs from the route. They're going down to be sent here. I'm not receiving BPDUs in this interface because that's facing downstream away from the root bridge. Again, if we look at the reason why this is the root port, they are advertising a cost of 0. I have a local cost of 19. So
You say they, what is they?
it's whatever device is on the other side of the link. So this link has a total cost of 19. This one has 19 plus 19, or 38. So this value is lower. This is why this one is being elected the root. Once we get down to the very last device, switch 4 we'll see now has equal costs to reach the root bridge. Where when we look at the show spanning tree VLAN 1 detail, the two ports that I'm trying to choose between are 16 and 19. If I were to go out 16, my cost on that link is 19. Their cost on the link is 19. So it's a total of 38.
38 to the root.
38 to the root, correct. So this is my cost to them, to the other side of the link. This is their cost to the root bridge. But the same is true on the other one, where my cost to the connected neighbor is 19. Their total cost to the root bridge is 19. So these two together are 38. Since these two are equal, now we need to look at the more detail behind the rest of the attributes. The next thing we look at is what is their bridge ID. So what's the bridge ID on the other side of this link? This is again made up of two fields. It's the priority and it's the MAC address. Since this value is lower, which is what I changed, 20,481 is lower than 32,769. That's why this is being chosen as the root port, and this one is now going into the to the blocking state. So again, the key is that when you want to change the path selection for the root bridge election, to change the election, we would change what? We would change the priority field, because that's the portion in their bridge ID. We have the priority, the system ID, and the MAC address. These two we can't change, so this one we're going to look at the lowest value. If we want to change the root port election, this is based first on what? The end-to-end cost. If there's a tie in the cost, then we look at the upstream bridge ID. If there's a tie in this value, we look at the upstream port ID. Where this last one is a tiebreaker if you have multiple links to the same switch. And you would choose whatever their lowest port number is.
How's the ether channel cost calculated?
It's the addition of both of the bandwidths.
Okay.
So if you have two fast Ethernet links and you bundle them together, it would be the same as saying bandwidth 200 megabits per second. So if we want to now change the path selection or ultimately how the MAC address table is built, normally what we would change is this. You can change the priority values, but it becomes kind of unpredictable what the actual end result of this is going to be. It's a lot cleaner to manage the network by changing the cost values. So let's say now that we first need to know, again, what does the network look like? So we have the root bridge there, which means that these two ports are designated. On the other side, those are the root ports. Switch 4 was then saying that number 16 is my root port. This one was root, which means that on the other side of that is designated. This one here was blocking, and this one was designated, because my cost value here of 19 plus 19 is higher than what their cost is. So switch 4 is sending BPDUs to the device on the other end of the link, So it's sending these advertisements to switch 3 saying my cost is 38. When switch 3 looks at this, it says that my cost is 19. And we can see that this at the top. It says that my route path cost is 19. Their route path cost was 38. It means that switch 3 is closer to the route bridge, which ultimately means that this is the designated port and this is the blocking port. But let's say we want to change the path selection, where we don't want to go this direction. We want to go this direction. When switch 4 is making its decision between these two interfaces, it's first based on what? It's first based on the cost value. We're adding 19 plus 19 versus 19 plus 19. This is going to work just like OSPF routing does, that you look at the cost value on your outgoing interface to reach the route. This means that if I change the cost value here, it's not going to affect anything. The cost value is only taken on the port that you would use to face the route bridge, your upstream facing interface. So this means I have a couple different options. If I were to raise this cost, if I move this to 20, then the end-to-end cost would be lower on this path, and the route port should change from this one to this one. Or likewise, if I were to lower this one, if I change this to 18, then the lowest cost still ends up to be this direction, and we would change over. Most of the time, the easiest way to do this is that if I'm trying to change the selection on switch 4, I'll just change one of these values. Because then it's easier to look at the configuration and know that I changed it for the purpose of the path selection. But the end result is going to be the same no matter how you do it. That you look at the lowest end-to-end value, however you calculate that or however you change it is going to be up to you. So this means we have a couple different ways to change the selection. Let's first look at, again, the show spanning tree VLAN 1. And mainly we're concerned about what these two interfaces say. This one is route, this one is blocking. The reason that I was looking at the show spanning tree detail is these numbers here only show you the local cost. So basically it's the cost of this interface. But it doesn't show you what the other side's cost is. So from here, it looks like these two are equal, but they're really not. The total cost on this one is 38. The total cost on that one is 38. I would see this if I scroll up a little bit further. That's what my end-to-end value is, the route path cost. So if we were to go to interface 19, and there's a couple different ways to change this. The cost itself comes from what? The cost comes from the bandwidth of the link. So if the link had a higher bandwidth, it would mean it had a lower cost. So I could say the bandwidth maybe of this link is 200,000 kilobits per second, or 200 megs. The result of this should be that the cost is lowered. Now the ports change their roles. Notice that the port state, it didn't immediately go to forwarding. It now has to go through the listening delay, then through the learning delay, and then after about 30 seconds, it's eventually going to go to forwarding. So each of these states are 15 seconds by default. So this is one way to change it. Since the cost comes from the bandwidth, if you change the bandwidth, it's then going to change the cost. The other way would be to change the cost directly, which is a little bit cleaner to do. You would simply say that the spanning tree cost value is whatever number you want to set, or you could change it on a per VLAN basis. This is the main advantage of Cisco's default implementation, that since you have different instances of spanning tree on a per VLAN basis, I could say that if I were to have two different hosts, or not two different hosts, two different VLANs. Let's say I had router 1 in VLAN 1. I have router 6 in VLAN 1. But then I also had router 3 in VLAN 2 and router 4 in VLAN 2. Since the path selection is separate, it's a separate instance of spanning tree, I could say that switch 1 is the root for this instance, and the path selection goes this way. But for VLAN 1, switch 1 is the root, and the path selection goes this way. So essentially, for different MAC address tables, you can have different choices in the network. And the way that you do this is by setting these attributes on a per VLAN basis.
Still have redundancy.
So you still have redundancy, but then you can do load balancing.
You talk about the trunk port.
The trunk port is what I'm changing, correct.
Okay.
So does enabling port fast allow all of this not to happen? Because it goes straight to listening? Excuse me, it goes straight to forwarding.
On the ports that go down to the end hosts, yes. So we'll talk about that next.
Oh, okay.
Okay. So if I were to change the cost value, right now this is a cost of 19. That's the default of this based on what the bandwidth was. So if I were to simply lower this, if I set it to 10, when I look at the change in the show spanning tree, this now is a cost of 10, which means that this is going to be preferred as the root path. But again, the port is going to have to go through this listening delay. So now if I go to router 6 and ping router 1, the traffic is going to fail until the port transitions to the forwarding state. And this is one of the disadvantages of the default implementation, that even though you're running the selection on a per VLAN basis, you're still using the original algorithm, which is based on the default hello timer of 2 seconds, the maximum age of 20 seconds, which means if the switch crashes, it's going to take you 20 seconds to figure that out. Then the forward delay is 15 seconds, so you wait for 15 seconds in listening, 15 seconds in learning, and then you can finally go to forwarding. So worst case scenario, if your connected neighbor goes down, it's going to take you about 50 seconds to figure that out. 20 seconds for max age to expire, and then each of the listening and learning phases. Question?
Yeah, does the port cost take precedence over OSPF cost?
They're unrelated, because this is talking about just the layer 2.
Well, I'm saying you have layer 3 enabling, right?
If it's a layer 3 port, spanning tree is turned off. So if we were to go to the interface and say no switch port, and then put an IP address directly on this, it means that it's no longer running spanning tree, because then the layer 3 routing process can take precedence over the path selection. But normally, if this is a switch port, that's going to be the default option. It means it's using spanning tree for the selection. So eventually, this is going to come back to the root port, because this is the lower cost value. So again, technically, you could change these other values. Like you could change the priority to try to change the selection. You could change that should say port ID. You can change the port identifier as well. The port identifier itself is made up of 2 subfields, which is a port priority and a port number. The idea behind this is that if the network looked like this, where switch 1 is the root, then I have a link that goes to switch 2, then I have 2 links that go to switch 4. When switch 4 does the path selection, it's going to say that the cost here is 19 plus 19, or 19 plus 19. So both of these end up being 38, which means that you look at this bridge's identifier. This bridge is going to be sending the same equal BPDUs out both of these ports. So it means that the priority value, the system ID, and the MAC address end up being the same. So you look at the port identifier on these two. And you basically would pick what is the lowest number port on switch 2. So the idea behind this is that if you want to have the control on switch 2, is the traffic coming in this port or is the traffic coming in that port? I could go to this link and say that the port priority is 0, and this one is going to have a default port priority of 128. Just like the root priority, you choose the lower one, where I would choose the 0 over the 128. But in a lot of cases today, there's no reason to do this. Because if you have multiple links between the switches, you would probably just do what? You probably just bind them together with a port channel. So if these are an ether channel bundle, from the spanning tree process perspective, it looks like one link. And it's going to forward over both of them based on some MAC address algorithm that the switch is going to figure out.
Does it load balance per packet or per frame? Or?
It depends on the platform. We're going to cover this today, but there's a command that is the port channel load balance. Basically, it does a binary operation between the destination MAC addresses, the source MAC addresses, the destination IP, the source IP, or both of them at the same time, and then it ultimately makes the decision.
But just wondering what's the delta between the failover using spanning tree and using the ether channel? Like if you were sending traffic and you lost one of the two links.
It's going to be immediate, because if it's a point-to-point link between the neighbors, it's something really, really small, like less than 1 millisecond it takes for the interface driver to figure out that the link is actually down. So if you have two links connected, like fiber links between the neighbors, and you physically cut one, it's immediately going to continue to forward on the other one.
That's using the ether channel, right?
Right, yeah, because what would happen is that the link leaves the bundle, and then when the switch does its load balancing, it just knows not to include that physical interface as part of the channel.
And the rapid spanning tree gives you how much convergence? How much time?
It depends. It depends on the failure scenario. We're going to talk about that today, though. So again, a really good resource on this overview of spanning tree is going to be that Cisco LAN switching book, where the syntax that it goes over configuration-wise is not relevant anymore because it goes through the old CAT OS, the set-based stuff. But the first couple introductory chapters that just talk about spanning tree are really good for this one. But this is the overall idea of spanning tree, that when there's multiple physical paths, we need to choose to forward over one of them, not all of them, because otherwise the frames would loop around the network. Now, as I mentioned, some of the limitations of this algorithm of spanning tree, the default, what we consider like the legacy algorithm now, is that when we're trying to do the calculation, there's a couple different states that we need to transition between. Where the link when it starts is going to be either disabled or it's going to be in blocking state. Where disabled means that it's like in the shutdown state or it's not plugged in. Blocking would mean that spanning tree had already calculated that it can't be used for some reason. So if we want to transition to a new topology, like something changes and then we need to change the path selection, we have to go through the listening and learning states before we go through forwarding. And the idea behind this is that the listening state is going to allow us to talk to the other connected switches and advertise our BPDUs. So I want to figure out before I start forwarding who is the current root bridge, and then do I have a worse cost or a higher cost to reach them. So I figure out which interface am I actually going to use for forwarding. Then we go through the learning state. This is where we start to insert MAC addresses into the CAM table. So we're trying to figure out where the host's located in the network. Once we go through listening, which is 15 seconds by default, and we go through learning, then we can finally go to forwarding, which is where we're actually sending the traffic. So regardless of which one you're transitioning from, if you go from disable to listening to learning to forwarding, Your best case scenario for this one is going to be 30 seconds. When you go from blocking to listening to learning to forwarding, typically you have to wait for the maximum age to expire. The maximum age is 20 seconds by default. And this is the amount of time you wait since the last time you heard a BPDU before you start to recalculate. So typically the case that this becomes useful is that if there's a software failure on the switch, but the physical link stays up, the switch is not going to know about that until the BPDU times out. And this is what the maximum age is used to do. If there's a physical link cut and the switch says that the link is now down, it doesn't have to wait for this max age. It knows to immediately delete the BPDUs, then go from listening to learning to forwarding. So generally there's going to be either two options, where you take about 50 seconds to reconverge or you take about 30 seconds to reconverge. Depends if you're coming from disabled or you're coming from blocking. These timer values are then going to affect how we transition between these states. Where the hello timer, this is how often the root bridge is going to send its advertisements out. This is going to be 2 seconds by default. Max age says that if I'm in the blocking state and I don't receive a hello time, or I don't receive a hello BPDU after 20 seconds, then I'm going to start to transition through the forwarding delays, which is listening and learning. So if you wanted to change the convergence time of regular spanning tree, these are the three that you would change: the hello, the max age, and the forwarding delay. These are going to be inherited from the root bridge. Where in this case on switch 1, if we look at the show spanning tree for VLAN 1, I'm the root. These are my timers that I have configured. If I were to change this where the spanning tree for VLAN 1 hello time is, let's say, 1 second, the max age timer is 10 seconds, and the forwarding delay is 5 seconds, it means that everyone else in the network is now going to use these new timers, because the root bridge is the one that sets the precedent for this. I'm generating hellos now every 1 second. They're going to wait 10 seconds before declaring their neighbors down. They'll take 5 seconds for each of listening and learning. So if we were to test this, let's say we go to router 6 and we do a ping that goes to router 1 with a timeout of 1 second. Every time we see a dot for one packet lost, it would be 1 second of convergence time. If we were to go to switch 4 and change the path selection, where right now we're going this direction, let's say we change it to go this way, where again I could do that by changing what values on switch 4.
Priority.
I could change the priority of these guys, or I could change the local cost values. So if I go to Fast Ethernet 16 and say the spanning tree VLAN 1 cost is 1, 6 should start to drop packets now for about 10 seconds. Where it was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 seconds. So give or take, it takes you a little bit of time to send a new update about the cost value, and then we had to go through the listening and the learning phases. And each of these I set on the root bridge to be 5 seconds. So the addition to these is 10 when we're going from blocking to forwarding. There's also another type of BPDU that I mentioned besides the configuration BPDU. This one is called the topology change notification. And in the case of the original spanning tree algorithm, it doesn't tell the network to try to recalculate. What it does instead is tell them to lower the aging time of the CAM table, or basically to try to delete MAC addresses from the table to try to build a new topology. And the way it does this is that every time we go from the forwarding state to down, or we go from the blocking state to designated, so if there's a change in the states, whatever device that happened on, there's going to be a new topology change notification. So let's say in this case that on switch 4, we have some new host that connects to the network, and this host is in VLAN 1. When this port comes up, when it's going from disabled to, it's trying to get to forwarding, switch 4 up the spanning tree is going to set this bit, the topology change notification. Eventually, this is going to get to the root bridge. The root bridge is then going to send to everyone else a topology change notification acknowledgement. This tells the other switches to set your MAC address aging time to be equal to the max age. Where we looked at this yesterday, it was some large value that the MAC address time was by default. If a TCN is generated, you set the MAC age time by default down to 20 seconds, which means that if hosts are not sending traffic, their MAC addresses are going to get deleted. So the idea is that you're trying to flush out the old information to build new information based on what changed in the network. So again, this is going to come from the downstream device. It goes out the root port. It goes up to the root bridge. So it goes to the next device. They send an acknowledgement. They continue to forward it out their root port. They get an acknowledgement. It's going to go up and up and up and up until it finally reaches the root bridge. The root bridge is then going to tell the other switches to try to age out their MAC address tables. And actually, I'm sorry, it doesn't set it to the max age. It sets it to the forwarding delay, which is 15 seconds, not 20 seconds. But the key is that you're changing it from a larger value to a smaller value to try to flush out the old information. The reason that this becomes a problem is that TCN is generated every time a port state changes. This means that if you unplug your laptop from the network, the switch that you're attached to generates a topology change. Or when you plug back in, it's going to do the same thing. It's going to generate a topology change. And this reduces the CAM aging time down to a lower value, which means that the MAC addresses get deleted.
Literally, when you put it full fast, it doesn't really...
That's the key, right? So if the switch, let's say the switch completely flushes out the CAM table, it doesn't know how to reach any of the MAC addresses anymore. How does it rebuild this information? How does it figure out where the end hosts are located? It has to do flooding. So for the unicast frames as they're coming in, it starts to treat them as broadcasts and it floods them everywhere. So the problem is that as hosts are being connected and disconnected to the network, it causes your switches to do layer 2 flooding. And you end up with broadcast storms at layer 2 as opposed to layer 3. So we'll talk about some of the different tools that you can use to fix this. One of them is a port state that Cisco came up with that is called port fast. It basically means that when you transition between these states, like from forwarding to down or from blocking to designated, that the port doesn't generate the topology change notification, because the idea behind this is that a port fast port is on the edge. It's connected to your end host, so you don't really need to do the recalculation. And this is the reason why it's recommended to put the ports that don't connect to the switches, you would want to put this in port fast state. And we'll see it has another usage as well, that when you go from blocking to designated, or when you go from, or not from blocking to designated, when you go from blocking to forwarding, or when you go from disabled to forwarding, you can skip over the forward delay. You can skip over the listening and learning phases. So you jump right between the two of these. because the idea is that that port is not part of the spanning tree anyways. It's on the edge of the network, so you can just automatically exclude it as part of the topology. But this was one of the original limitations of large layer 2 switch networks, that as you start to add hosts or remove them, it's going to flush out the CAM table, and then you end up flooding your traffic everywhere in order to rebuild the MAC address table.